Thank you very much for the introduction, and thank you in general to the organizer for inviting me today. It's a pleasure to be here and celebrate this wonderful journal. So there is a switch in subject. We go from magnetism mainly and spintronics to quantum thermodynamics, and I will also be talking about density functional theory. I like to work at the intersection between fields, and this is an example of it. My research in this field has been funded during the years from different sources. And I've added the cast for because I'm still really working on this, and I'm still trying with collaborators to devise functionals for quantum thermodynamics, as well as doing progress within quantum thermodynamics itself. So let me start to tell you a bit about the type of physical processes I'm interested in this context. We have a system, is a many-body system at finite temperature, and we start from thermal equilibrium at a certain Hamiltonian H0. And then we detach the system from the bath, so we will have a closed system, and we will drive the system. What does it mean, driving the system? It means, for example, to change the external potential of my system. It means to apply an external electric or magnetic field. It depends a bit on your setup. And we drive the system for a time tau until the Hamiltonian becomes h of tau. And in this dynamical process, we can either extract work or give work to the system. In general, we will have a change in energy for our system. Our Hamiltonian is time dependent. And we will end up in a many-body system. We haven't lost the bodies. We have conservation of particles, but we are out of equilibrium. We will be out of equilibrium, however slow our dynamics will be, because we are in a closed system. So at this point, we can decide to attach our system back to the bath. Thermalize. Thermalize means having a dissipative process, so we will have exchange of heat with the environment. And in this way, we will end up at a new thermal equilibrium, now in equilibrium with our Hamiltonian h tau, so with a different, if you like, external potential. And from here, we could go back and finish a cycle. So this is the type of protocol of quantum thermodynamics, QTD protocol, I'm interested in. If I want to calculate or measure work, I will also have to deal with measurement, projective measurement of my quantum system in the basis of the initial and the final Hamiltonian, which complicate things. And so I'm dealing with a system that is a bit a nightmare, the nightmare for a theorist. It's a many-body system, it's interacting, I have finite temperature, I work out of equilibrium, and I have also some irreversible process. So the point is, can we find good ways to, good method, efficient method to doing calculation within this complicated protocol? Because of my background, I like density functional theory, and this is the type of methods I am trying to develop over the years. So let me just tell you a few words about density functional theory. It's quite an old theory now. It started in the 60s. It got a Nobel Prize for chemistry. Walter Kohn got a Nobel Prize for chemistry, I believe it was 2007, but I may be saying the wrong year here. And the idea, the great idea of density functional theory, is an idea supported by theorems, is the fact that instead of calculating properties of a many-body theorem by basing my calculation on the many-body wave function, and so doing all the calculation using the full many-body interactive system, I can actually, through the theorems of density functional theory, do my calculation using a non-interacting system known as the constant system, which has the characteristic of having the same density, local density, as the original interacting system. And then, if I'm able to write explicitly or approximate the quantities I'm interested in, so in general, this will be mean values of certain operator in terms of these densities, then in order to calculate these quantities, I simply solve, simply in inverted comma, but it's simpler than solving the many-body interacting system. I solve the constant system, and then I can calculate my estimates. So big simplification. So now if I want to apply this theory to quantum thermodynamics, same cycle as before, I start to have some issues, because as I move around my protocol, I see that I can imagine that some property will be functional, if I can write it, of the initial equilibrium local density of the initial Hamiltonian. But then I have dynamics, so maybe I have to go to thermal TDDFT, not completely developed at all, but there I will have other type of densities coming in. There will be time-dependent densities out of equilibrium. But then I want to have projective measurements if I want to calculate the work. So how do I embed this with this density functional theory formalism? Which are the densities that are important, which are my dependencies, even worse with irreversibility. And so the key point, the key questions are, can I indeed use efficiently, can I use at all, or can I use efficiently density functional theory or ideas from density functional theory to tackle this type of problem? Which are the dependence of the functionals, if I can find them, which are workable approximations for this functional. Once I have this functional, I also want to do actual calculation. And so I will tell you a bit of where we are with this. I will just give you some results at the end. But before that, I'd like to tell you about quantum thermodynamics, why it's interesting, or at least why I find it interesting. And then I will tell you a bit about the model system that I will use for the calculation and some of the results for that we have found with this type of system. So, quantum thermodynamics. First of all, in contrast with the thermodynamics we are used to, we are dealing with small systems, small quantum systems. This means that we are dealing with a few degrees of freedom, and we are very far away from the thermodynamic limit. So it's a different, very different setup. In this small system, I cannot take for granted thermalization, especially if I'm in a closed system, because I have a very fine, reduced number of degrees of freedom. When I talk about a working fluid, I may even refer to just a single qubit, so just simply a two-level system, or a small molecule, or a small example of qubits or two-level systems. And at this level, quantum effects have a very strong effect. So together with thermal fluctuation, which we are familiar with in standard thermodynamics, we will also have quantum fluctuation, which, for example, will enter due to measurements, projective measurements, for example, of my system. And there are many questions. Among these, what are the role of initial coherences, for example, in my quantum system? Or the role of quantum correlations such as entanglement, the role of many-body interactions, and so on and so forth. Even just concepts like work or heat, when I want to define them at this level, there's still some question mark on them. So concepts that sound so familiar to us in normal thermodynamics become open for discussion when we go to quantum thermodynamics. So, as an example, thermodynamics is a kind of statistical process. I will have a probability distribution when I think about the quantity I want to explore. And the typical thermodynamics probability distribution is something well behaved, as I have sketched here. So something akin to, for example, a Gaussian, a bell-shaped function. Usually it has a well-defined maximum, which gives me the mean value I'm looking for is usually narrows, and the width is given by thermal fluctuations. Of course, I also have the experimental noise, but being a theorist, I can say I will have the thermal fluctuation and I forget about the noise. Well, I don't, but anyway. We go to quantum thermodynamics, and our probability distribution function has a completely different shape. As I said, we have small quantum systems, which means I have to look at a finite number of transitions between quantum transitions, so transition between energy levels. I have a distribution which may be asymmetric, may not have a single maximum. The width will be defined by the allowed quantum transitions, and it will be dominated by quantum fluctuations. And I can have all sorts of effects that will affect this transition. These are just some reviews or introductions about quantum thermodynamics, but by now there is a lot out there. So this is by all means non-exhaustive as a type of list. But just to give you an idea if you're looking for a review or an intro. I will mainly focus on work on this talk, so let me also emphasize what is the difference between work as we are used to and work in the quantum world. So when we talk about work with a macroscopic machine, for example, we can think about a piston which will somewhat lift the weight, and in this way it will change the energy of my weight, I will have some dissipation, and it will anyway be able to produce work. When I look at my small quantum system, what I really look at are elementary energy transitions. So in the most minimalistic case, I can look at a two-level quantum system, and I can look at the transition between excited and ground state as a way to extract work from my two-level system or to give work to my system. So when I talk about average quantum work, which I will do, what I have in mind is either the average over many samples of my quantum system or a repetition of my protocol many times on the same system. And let me now put a bit of these concepts together. So we have our thermodynamic protocol. And in particular here, I have rewritten what you've seen in the first slide up here. So I start from this state thermal equilibrium, I drive my system, and I end up in a non-equilibrium state. I want to calculate the average work, the mean work, so over the statistics that I can have from this process. And so I have a work distribution function, which will be given by this object, which will include the probability of being in a certain initial state of the initial Hamiltonian, the probability that my dynamics will induce a transition between an eigenstate of the initial Hamiltonian and an eigenstate of the final Hamiltonian, and of course, conservation of energy, because I'm dealing with a closed system. Okay, so my probability distribution for the work will include all these elements. How does it look like? These are results from simulations done on doesn't matter. I mean, I will talk later also a bit more about the system. Anyway, this is a number chain. But the key point is this is the work. So each of these is a probability distribution for the work done with a different dynamics. The shape, in fact, of my probability distribution depends a lot on the dynamics that I use to go from the initial to the final Hamiltonian. So here I have a sudden quench probability distribution. At the opposite side, I have a quasi-adiabatic probability distribution. You can see that I have a discrete set of peaks, but you can also see that some of the transitions that are strong in the sudden quench may be less strong when you have a slower dynamics, and vice versa. Some of the transitions that are very small in a sudden quench may become very important when you go toward adiabaticity. So the shape of PW is strongly affected by the dynamic regime. The type of system I will be looking at, though is not the only system for which the theory we derive works, is a driven one-dimensional Hubbard model. We have a bit looked at the Hubbard model with our first speaker. So in the Hubbard model, we have a hopping term, which tells me that my electron can hop from one side to the next. We have a on-site interaction term, and we have an external potential. This is the part that is driven here in order to induce the dynamics. And what is interesting about this system is that we can have phase transitions. So there is a phase transition that is the metal to mott insulator transition that is induced by the interaction, by the on-site interaction. I will talk about the precursor to this transition because I will be looking at finite chain, finite length chain, but also using the external potential, I can induce a transition from a metal to a band insulator. Okay, so I go to an external potential which is quasi-homogeneous, to an external potential which is really comb-like. You see this big zigzag when I'm out here. And in this way, I can induce this type of transition. These two transitions are in competition, and so this makes it interesting as a type of dynamics. In general, we have that when I look at work, this is work calculated exactly for a chain of 6 sites against the interaction. We can see that interaction, voila, that interactions actually affect a lot the work that can be extracted. If you fix U and you go across, you see that the work changes a lot, depending on your type of dynamics. So I will now go to our results in relation to combining quantum thermodynamics and density functional theory, the recent results. And these are contained in this paper, and Antonio is a bit the star of this work. He is a PhD student and did a lot, not only of the calculation, but also of the theory derivation, which I'll be talking about. So we want, again, to express our quantities for quantum thermodynamics as functional of the thermal density, thermal equilibrium density of the system, in the spirit of using the densities, the local density as the key quantity for calculating my operators, mean value of the operators. And we want then to find also the functional, and we want to find approximations for the functional benchmark and then get new results. To do this, we base, because we are now a finite temperature, we base our theory on the Merming-Onenberg-Kohn theorem. And the key point of the Merming-Onenberg-Kohn theorem is that establishes a one-to-one relationship between what? Between, this is now my Hamiltonian, is similar to before, but it's more general. It's the Hamiltonian on a lattice. This is my external potential. These are local operators. For example, could be the local density operator, the local occupation operator. And these are a driving parameter for my external potential. So these are numbers, okay? And I have a one-to-one correspondence between this set of numbers and the local densities, the generalized densities, defined in this way. And also one-to-one correspondence between this and the thermal state at that temperature. This one thing I'd like to stress. If I think of this, this is a matrix, if I want to express it. And so this is a matrix, let's say an n by n matrix, but this is just a vector. So I'm losing a lot of degrees of freedom of going from here to here. Nevertheless, I have the same information. This is the strength of the Onenberg-Kohn type theorem, in particular, in this case, at finite temperature. So the game is now again find explicit functional for the quantities of interest, explicit functional in respect to my generalized densities, and then use this correspondence. Use the Mermin-Koncham theorem to calculate these quantities, and then from here, from the function, I can calculate the mean value of the operator or the quantities of interest. So the first quantity we looked at was the Helmholtz free energy, and we showed that it can be written as a functional of our generalized density, local density, but in particular, the derivative with respect to the potential driving parameters, driving potential parameters of the free energy is actually given by this local density. And this is very nice. Then we looked at the work probability. We have seen that the work probability is a key quantity if I want to calculate quantum thermodynamic properties related to work. And however, it's not an operator. Work actually is not an operator. So it's not a given that I can write it as a functional of the state, and then from there as a functional using the Mermin-Onenberg-Kohn theorem as a function of my generalized density. So there was a bit of work to be done there. We could demonstrate that, sorry, I went that much. We could demonstrate that, in particular, all the moments of my distribution are indeed functionals, formally functional or functionals of the generalized densities. And we can write explicitly these functionals for the first moment, which is the average work, for the second moment, which is the width of my distribution. And this is in the case of the sudden quench and the infinitesimal sudden quench. So the other question was, can we do irreversibility within density functional theory? So even worse, except luckily we know that there are fluctuation dissipation relationship that we can use, and this helps a lot. And so through that we can connect equilibrium quantity to dissipation, and we can indeed demonstrate the reversible entity that characterize here the residual lag that characterize the irreversible step within my protocol can also be written in terms of my generalized densities. And so from here, we can know that at least we can use density functional theory for this aim. We have the explicit form of this functional for the case of an infinitesimal sudden quench. And so now we have our functionals, and we have explicitly the functional in terms of the quantity I can actually calculate. I can calculate the quantity using the Mermin-Koncham system and scheme. And that's what we have done. We have done the benchmarking against, using the inhomogeneous Hubbard chain, which I've discussed before. And for who knows a bit more about density functional theory, we have worked with functionals. We have adapted our functional to a type of LDA approximations. And let me show you the results. So first of all, I have a comparison for the results for the work, for the extracted work, and also reversible entropy for an Hubbard dimer. The quench here, the sudden quench, is done by increasing the size of inhomogeneity. And we start from a system with this type of inhomogeneity. I only have two sides, so it's just the first two sides, really. And the initial inhomogeneity is given here, and this is the U is the on-site many-body interaction. And you can see that in the In the band insulator region, so when this is quite wide, I can extract work, while when I'm in the Mott insulator region, so when this is basically homogeneous, basically it cannot extract work, there is a transition region. And this is very well described by the reversible entropy. And when I looked at our thermal DFT results, I couldn't really distinguish them because they are basically the same. I mean, you can see 4 significant figures, basically. It's a very good approximation for the dimer, okay? So we go to longer chains. Now the potential so now we have a finite size chain between 2 and 8, and a chain that I can solve exactly for benchmarking. And the type of driving is a bit different. So I start again from an inhomogeneous, slightly inhomogeneous system, and then I tilt it more. I have a linear potential. And once more, you see that the difference, these are the local densities, okay? The difference between the exact and the results from the Conchamp scheme, Mermin-Conchamp, are very little. So again, we can trust our functionals and our approximations to the functional. Also, when we test the result, not just for the densities, but also for the average voltage. And with this, we can go and, I've almost finished, thank you. We can go and then find some new results, analyzing structures that could not be exactly diagonalizable. So in this case, these are longer chains, Hubbard chain. This is, again, a slope potential where we have that in the Mott insulator phase, we cannot really extract work. So we are again tilting our potential. Here we have instead an harmonic potential, which we are opening. Okay, so this is my confining potential, and this is my sudden quench. And what we find is that here, on the contrary, when we are in the Mott insulator phase, we can actually extract more work from the system. So this is an interesting result. Let me thank my collaborators, in particular the one in blue are the ones that have contributed to this particular results, Antonio Calamara, Francesco Plastina, and Nello Sindona. I have an opening. If you have a very nice candidate for a PhD position, send it to me, please. And these are the conclusions. So I have discussed, I introduced concept from quantum thermodynamics and density functional theory, and I showed you how we have managed to expand thermal DFT in order to encompass part of the quantities that are important for quantum thermodynamics, including quantities that describes the dissipation part of the thermodynamics protocol. And here are other works that I have done with other collaborators that I mentioned before on this subject. So thank you very much for your attention.